All right, so our goal for this first part here is to learn everything there is to know about, everything you need to know about projective geometry. And the brief motivation here is that ultimately the picture is going to be something like that in kinematic space. So in the space of Mandelstam invariance, or what we'll talk about for the amplitude in momentum twistor space, we're going to be finding certain geometric regions, okay, like the insides of polygons or polytopes or fancier things of this sort. But they're going to be certain bounded geometric regions. So these are the positive geometries that we're going to be talking about. And the reason for the name will become obvious as we go along. But these are spaces with the property that they're some sort of compact region, and they're bounded by faces, by walls, boundaries of all possible dimension, right? So in this case, the object itself is the inside of a polygon, is two-dimensional, but it has edges that are one-dimensional, and also vertices that are zero-dimensional, okay? That's just to give a distinction. A circle, from this point of view, is not a positive geometry. It has an inside, which is two-dimensional, and a boundary, which is one-dimensional, but it's missing the zero-dimensional boundaries, okay? So for something to be a positive geometry, it needs to have boundaries of all possible codimension going down, and a few other conditions that we'll talk about. But let's just stick with these more familiar intuitive things for now. So there's going to be some geometric shapes, and these geometries are going to have their own raison d'etre, right? There are zillions of geometries you could write down, but there are natural, combinatorial, positive questions related to the positive Grassmannian and other things, but where, even without any knowledge of those things, there are some natural questions, fundamentally combinatorial questions that you ask in these spaces that pick out these interesting geometric regions. So that's part one. There are some interesting geometric shape. But part two is, ultimately you want a function. You want to get some juice out of this, something that you can tell your experimental friends about, right? So how do we get functions out of this? Well, we don't get functions immediately, but these things are tied in a very important way to a certain, so this is a positive geometry, and it's a real geometry. Okay, it's positive, so it's real in particular. But tied with this is a certain differential form, a canonical form. And this differential form, it's a top form that lives on this space, but it has the properties that it's determined by having so-called logarithmic singularities. So if this positive geometry is P, there's a differential form that goes along with it, which have the property of having logarithmic singularities on all the boundaries, on and only on all the boundaries of P. Okay? So, and we're going to talk in detail about what this means. But this is just as motivation for where we're going. So the kind of objects we're going to be looking for at infinity are positive geometries. And the scattering amplitudes are going to be associated with differential forms. So these differential forms are kind of a slave to the geometry. Okay, so there's and it kind of goes forward and backward. If someone hands you the differential form, and this is in practice the way all these things were stumbled upon. We didn't know about any of these things for half a decade, okay? But the way we stumbled onto them is that we had the amplitudes that after some time were put in the form of kind of looking like differential forms. And we had this great clue from Andrew Hodges to think about the poles of the forms as kind of facets of some geometry, and think about how they glue together as telling us something about how these pieces glue together. But the whole time, the existence of the functions and the forms were kind of hinting at the existence of objects like this, which we then finally found. Okay, so, and once you find them, so these things are very closely tied to each other. Okay, so that's our the broad sort of thing that we're looking for, but in order to describe these geometric things, it's most convenient, and actually immediately it's handed to us by things that live in a projective space. So, and in Grassmannians, even generalizations. Although in what we're talking about today, with everything living in kinematic space, it really is just in projective space. And so, so let's start talking about how to think about all this geometry in the simplest possible way. And and this is our crash course introduction to projective geometry. Okay, so So the general rule of life is that any geometric question that does not involve a metric, does not involve distances, angles, any geometry problem that so what kind of things are left if we don't talk about angles and distance and so on? You know, if you have 3 points, and if you can talk about angles and distances, and it makes sense to ask how close is that point to that point, or what is this angle, and so on. There's millions of questions that you can ask. If you're not allowed to ask about distances, okay, if there's no notion of distance or angle, then the only questions that you care about are, you know, let's say I'm giving 3 points on the plane. Then the only things that matter are notions of incidence. So like these 2 points define a line, and you can ask whether this third point is on the line or not on the line. Okay? So it's that question and generalizations of that question which are what projective geometry is all about. Okay? So it's ultimately about statements that have to do with notions of incidence. Okay? All right. Now, you could study these questions. So I draw two-dimensional points on the plane, and everything is perfectly fine. Nothing forces you per se to talk about them projectively. What does talking about things projectively mean? It means that instead of talking about a two-dimensional vector x, let's say, or a collection of two-dimensional vectors x, I uplift this to a three-dimensional vector. Okay, where that index I now goes from 1, 1 to 3. Okay, so I'm just first saying you pragmatically what it means. We'll talk about it geometrically in a moment. Of course, in doing that, I have to say that to go back from 3 to 2 degrees of freedom, I have to say that I'm identifying x and any multiple of x with each other. Okay? And so if you do that, you can always take, so if this x look like, you know, look like x, z, x, y, I can always, I can say that this is the same as 1 x over z, y over z, just by scaling out z, okay? Or maybe I should have called that z, or CAB. Then I could make the 1 a over c, b over c, which I can call 1 xy. Okay, so this is how we go from three-dimensional vectors up to rescaling to two-dimensional ones. Geometrically, what does this mean? Geometrically, it means that we're studying the space of all lines that pass through the origin, in this case in 3 dimensions. Okay? So if I look at a vector modulo rescaling, a vector modulo rescaling is just giving me a line that passes through the origin. Okay? All the points modulo rescaling are just points on that line. And so my objects in this space are lines that pass through the origin. And now I can intersect this picture with any old plane that I like. Okay, if I intersect it with any old plane, I get some configuration of points. Okay? So that configuration of points is exactly what I'm talking about here. In fact, what I've done here, if this is the z direction and the x and the y directions, is exactly do a plane in z. Okay, so when I chop it in a plane at fixed z, then the places these lines intersect, the places at fixed z are what I call those coordinates x and y. Okay? In practice, just so you know, in practice, when you're thinking about like two-dimensional projective space, just think in terms of points in a plane. Okay, and you'll never get anything wrong. Just think naively in terms of points in the plane, and you'll never get, and everything will be fine. Now, let me just say some of the immediate practical things, and then the deeper underlying reason why this is a good thing to do, which is really actually discovered by Newton, even though projective geometry was, of course, introduced by artists and mathematicians roughly simultaneously in the 1500s as they were learning to draw pretty pictures in perspective. But let me say, one immediate thing of practical importance is that this picture allows me to talk about things in a slightly more uniform way than I would if I was just drawing pictures in the plane. So, for instance, this is a famous fact. So we know that two generic lines in two dimensions intersect at a point, but I could have two parallel lines. Okay? So you might like to have the statement, any two lines intersect at a point, but it's not true, right? There's a special case of parallel lines, right? Now, in this picture, it's clear that anything will, any set of lines will give me something that intersects. It's just that the intersection point might not be captured in this particular coordinate chart. Okay, so when I say I can take the top component of z and scale it to 1, I can do that provided that z is not 0. Okay, but that means there's a part of the space where z is 0. The part of the space where z is 0 is not captured by that coordinate chart. It's there, it's just not captured by that coordinate chart. Is that clear? Okay. Now, what does z going to 0 mean? Z going to 0 is, z becoming tiny compared to the other ones is just like sending x and y and sending them to infinity. Okay? So that means that there's a whole part of the space which is being thrown out when I draw these normal two-dimensional pictures. There's something else at infinity which is being added when I think in the language of lines through the origin. Okay? But that means that projectively, in the projective space, any two lines do meet at a point. It's just that point might be on a whole line at infinity. Okay? Is that clear? Now, just so you don't worry, you never actually have to spend your time thinking about these or you very quickly get used to doing it anyway. Mostly what it's useful for are, and it's for the following deeper reason, are actually doing real manipulations with these geometric objects and keeping track of what they do, regardless of whether you're in special configurations where they intersect at infinity or not. So let me now more quickly say the deeper reason why projective geometry is important. It's the answer to the following quite invariant question. Imagine I just give you points on a plane. Okay? Now you can ask, what are all the transformations I can do on the plane that have the property that they map straight lines into straight lines? Okay? Now, there are some very obvious ones. There's 2x2 linear transformations, map straight lines into straight lines, and translations map straight lines into straight lines. Okay? And that's naively what you think that's everything there is. However, it's wrong. There's actually a larger set of transformations that map straight lines into straight lines. Okay? So in other words, if you give me x and y, two-dimensional x and y, one set of transformations are this, so that's SL2. The other one is xy goes to xy plus alpha beta translation, so this is two translations. Okay? So the naive transformations that map straight lines to straight lines is SL2 cross T2, but in fact there's a much larger set which is an SL3. There's an SL3 that maps straight lines into straight lines. And we can actually write down what it is directly on x and y. But it's much more convenient to say what this SL3 is projectively. Okay? Because projectively, it's just xi goes to Lij xj for L in any 3×3 linear transformation. Okay? You see, that clearly maps straight lines into straight lines in the underlying picture of lines through the origin, and therefore it's guaranteed to map straight lines to straight lines when you intersect that with a plane. But it's an unobvious symmetry of the plane. It's actually a nonlinear symmetry of the plane. And you can work out what the symmetry is just by taking the general matrix, acting it on x, and rescaling the top component of x to 1, of capital X to 1, to work out what it looks like on lower x and y. So that's an exercise I'll leave for you. Okay? But this is the invariant point, that the symmetries of the plane that map lines to lines is not just the obvious ones of SL2 cross translations, it's these larger ones of SL3. And this picture of points on the plane as being associated with lines through the origin in one higher dimension is the picture that linearizes the action of that SL3. Okay? From this point of view, you see it's a lot like grand unification. It's a lot like spontaneous symmetry breaking. In fact, Felix Klein, one of the greatest mathematicians of the 1800s, I think understood this business about symmetry breaking and grand unification in the way we think about in particle physics 100 years earlier, or 80 years earlier. And he actually understood that you could think about all the geometries that people were talking about back then in this language. He actually began with just two-dimensional projective geometry where the symmetries are SL3, okay? But when we say that we put the top component to 1, when we put the top component to 1, it's like we take the equation xi, and then we put something else. Let me call it y just for a moment. And we say that we're setting x dot y equal 1, okay? Where this y is like 1, 0, 0, okay? So when you're just talking about this coordinate patch, giving this coordinate patch is as if you've given a dual vector, one with a downstairs index, and you've specified it to be a fixed value, 1, 0, 0. Okay? We'll come back to interpreting these things with downstairs indices in a moment. But if you ask, what are the SL3 transformations that leave y fixed? Okay, that's not all of them. That's only a subgroup of them. And the subgroup is exactly SL2 cross translations. Okay? So it's a lot like guts. If you have an object that breaks a symmetry, then only a subset of all the symmetries keep it fixed. Okay? But if you see that and you move that guy too, you restore all the symmetries. Right? So just like in grand unification, quarks and leptons look different from each other, but in the underlying SU5 they're unified. If you also move the Higgs vev that Higgs the SU5 down to the standard model. So here, what is the analog of quarks and leptons are parallel lines and non-parallel lines. Okay? So parallel lines, they transform into each other. Non-parallel lines transform into each other. But the larger SL3 moves them around, and it transforms parallel lines into non-parallel lines and so on. Okay? What does parallel mean from this point of view? It means that there's this, well, I'll explain this in a moment, but this y is really a line at infinity. And two generic lines meet. They might not meet at infinity. They might meet at infinity. Okay? But there's no deep difference between these things, and if I move everything around, I can change whether or not these intersections take place. All right. Okay, but anyway, so that's the deep reason projective geometry matters, is that the symmetries mapping lines to lines is actually larger than the obvious one. Okay, But now that's all about general theory. Now let's just use it, because it's incredibly powerful and easy to use. And that's what I want to spend the next 20 minutes or half an hour talking about. And this is, if you want to think about geometry of scattering amplitudes along the lines that we've been talking about, it's the exercises that I'm about to show you that are what you need to know how to do. Okay? So let me tell you. So let's start doing some simple exercises. So first, I just said that x sub I upstairs are points. Okay? Now, let's go back in an old-fashioned way and think about how would we describe a line in the plane, right? A line is something that satisfies an equation that looks like ax plus by plus c equals 0. So this is a line. Okay? Okay? Or what about a conic? A conic is, now I'm going to get bored, ax squared plus by squared plus cxy plus dx plus ey plus f equals 0. This is a conic. Right? And you see how annoying these equations are, right? There's a part that multiplies x and y. There are these constant pieces. There are things of different degree here, and so on. But projectively, these are much prettier statements. What does that mean projectively? It means that, for example, if I go think in terms of the line, I really think of that equation as being ax plus by plus cz equals 0. So I put a z back into that last component. See, now this equation is homogeneous under rescaling x, y, and z. So I could, if I wanted to, rescale it back to set z equals 1, and I go back to the old description. Right? Okay? But in this way of doing things, I can write this as xi, yi, or let me write it as li equals 0, where L would, in components, just be A, B, C. Okay? So is it clear? This has an upstairs index, and this has to have a downstairs index, because the only symmetries we have here in this problem are SL3, nothing else. There's no metric. The only invariant tensor is the epsilon symbol. Okay? And so x is projective, because I could rescale x. Also, L is projective, right? I could rescale A to 1, or B to 1, or C to 1, and so on, right? And part of the beauty here is that you don't have to worry about the special cases where A is 0 or B is 0, or they're parallel, they go to infinity. Everything is just taken care of uniformly. Okay? So, in summary, something with an upstairs index is a point. Something with a downstairs index is a line. Okay? Is that clear? Is it clear what I mean by that, right? So if you give me L, let me say it another way. If you give me these three numbers L, there's a whole bunch of x's that satisfy this equation. All those x's are on a line. If you give me a line and you give me some point, and I want to know, is that point on the line? I shove it into this equation and check if x dot L equals 0. Okay? All right. Now, just for fun, since we're at it, what do you think a conic is? Hey, to make a conic, I would go and I would just shove in z's everywhere I need them. There's a z, there's a z, there's a z squared. Okay, and so a conic is a c with two downstairs indices that's symmetrized, right? So the equation for a conic would be xi xj cij equals 0. Okay, and so this is symmetric in the two x's, and so Cij is a symmetric matrix. Okay, so this is a conic. All right. So far, so good? Okay. Okay, but now let's have some fun. So, let's say I give you 2 points. Here's a point x, I, and some other point y. These 2 points define a line, right? So what is that line? How do you figure out what that line is? Now here's the really simple thing. You don't have to think. You know what the object is you're looking for. You know what kind of indices it has. So you just take the things that you're given and put them together in any way you can to give you the right indices. And it always is correct. Then you check if you want to impress your math friends. But if you're a physicist, you can stop at that point and just declare victory, right? So here, I have to get something with a downstairs index, right? Because the line has a downstairs index. So how do I take two things with an upstairs index, x and y, and get a downstairs index? What's my only invariant tensor? Because the symmetry is SL3. Just the epsilon symbol. So that's it. It has to involve x and y. And so there's a line Li, which is epsilon ijk, xj, yk. Isn't that nice? Okay, so you don't have to sit there and solve two equations and two unknowns to figure out whether, in fact, that's solving the two equations and two unknowns for you. Okay? This is Cramer's rule, except you don't have to think. Right? You just write down the answer. Now, let's actually check that it's true. Is it true that x is on this line? Well, why, yes, it is, because if I contract this with x, the epsilon symbol is antisymmetric. There's two x's, so it kills it. Okay? Similarly, y is on it. All right? All right? That's cool, right? So let's keep going. So let's say someone gives you 3 points, x, y, and z. And I want to know, are these 3 points on top of, are they collinear or not? Okay. Well, what does it mean for them to be collinear? It means that z would have to be on the line made out of x, y. Or the other way around, in any combination of them. So you don't even have to think that much. Because now I'm asking a question about 3 points, and I'm not looking to get an object out of it. I'm looking to get an answer to a yes-no question. Are they on a line? Aren't they on a line? So I have to make a scalar out of these guys. Okay, so how do I make a scalar out of them? I just have to contract them with an epsilon symbol. Okay, so I have to look at the object bracket x, y, z, which is epsilon ijk, xi, yj, zk. Okay? Of course, notice that I can interpret this object as checking whether x is on the line made from yz, or y is on the line made from xz, or any other way that I like. But there's actually a symmetric invariant object between all three of them. And so what does it take for the 3 points to be collinear? This has to equal 0 if x, y, z are collinear. Okay? All right, let's keep doing some of these elementary things. What if we have two lines? What if we have two lines, L1 and L2? Well, two lines intersect at a point. Okay? So again, who is the point that they intersect at? It's exactly the same, right? I have to take these two. Now they have two downstairs indices. I have to make an upstairs index. So it's L1, L2 contracted together with an epsilon. Okay? So I can write it now as epsilon ijk, L1j, L2k. Okay? So that's the intersection point. What if I want to check whether three lines are collinear? If they're like that, or are they like that? Sorry, whether three lines are, what I don't know what it's called, copointular, whether they all pass through the same point. Okay, then if I want to check this, then I'm just calculating this L1, L2, L3. And as time goes on, we're going to stop writing these epsilons all the time, right? When it's clear what you mean, whenever you take objects together, when there are indices left, you're just always anti-symmetrizing them, okay? So for instance, we could just write down, just like I could write down x, I don't even put the index. I'll still be a little responsible to put the index now. L downstairs, but I can write down L1, L2 upstairs. And I know exactly what I mean by that, right? Everything is just contracted in the only way it possibly can be. Okay? So absolutely minimally, never in your life again should you solve equations and unknowns to find where lines intersect. Okay? If you do, you should be ashamed of yourself, right? Because you can do it projectively. All right. So now let me just whet your appetite a little bit. I won't solve this problem for you, but all these things are still basically trivial. But this is an exercise for you. And there's a really wonderful book that David Hilbert wrote in the early 1900s called Geometry and the Imagination. It's for the general public. The nicest copy of this book that I have, I owe to Jake Bergeli here, who gave it to me as a. I don't know why you somehow gave me a present for graduating, but anyway, that was a good deal. Actually, Yara didn't. Oh, you did actually. Yes. Yeah, it was vodka though. I like Jake's better. I like Jake's better. Sorry, Jake's. I haven't even drunk your vodka. Yeah. Anyway, it's a huh. Sorry, yes, it had your name, but apart from that, you know, it's not like Geometry and the Imagination, which is cool. Anyway, this is an incredible book. You should read it if you can get your hand on it. It's for the general public, but it has all sorts of deep geometry. And in this book, Hilbert calls this problem the first non-trivial theorem in geometry, essentially. Okay, and actually it goes back to Mr. Pappas. I assume it was because of the rampant sexism in Greece, I assume it was a Mr., but who knows? Mr. or Miss Pappas, who noticed the following thing by looking at shadows cast by trees in olive groves. If you have 3 points that are on a line, 1, 2, 3, and other 3 points that are on line A, B, C, then if you make the following composite points, so you take 1B intersects 2A, so there's a new point here. If you now make 2C intersects 3, the chances it's going to work are so low anyway, but not if I do that. 3B intersects there, and then I do 1C intersects 3A, and it's there. Anyway, Pappas observed that these 3 points are collinear. That's why I've never once in my life done this right. Okay, so Pappas observed that those 3 points are collinear, and you can prove this, you know, various standard geometric ways. But here's an exercise for you to prove it using the techniques that we just talked about, right? So and in fact, if you don't want to think, just go to Mathematica, put in 1, 2, any coordinates, make 3 a linear combination of 1 and 2, so that it's on the line. Put A, B, any coordinates. Put C, any linear combination of A and B. And then just build these things from the determinants. Tuck, tuck, tuck. Put the giant determinant and just see everything cancel out and get 0. Okay? So this ability to prove these geometric statements algebraically was one of the things that the 1500s and later mathematicians found attractive about this formalism. Okay. Let me give you one more example. Just we won't deal with curvy things so much, but just because it's fun. And since we talked about it, let's say you have a conic. Okay, so here's a conic, and so here's a conic C. I'm going to choose a point x star on the conic, and I want to know what is the tangent at x star. What's the tangent to the conic at x star? Now, maybe you guys are tough guys, but I'm sweating at this point. Okay, I'm like, oh shit, what am I going to do? Take some derivative, figure out the tangent. This is like, I'm slightly scared, right? If you're not scared, you're tougher than I. But okay, let's do it now. So, what do you think the tangent is to the line? So, what is the data at our disposal? So we have the C with 2 lower indices. And we have a point x star on the lines with an upper index. What am I after? A line. So what do you think it is? Don't be afraid. Just contract them, right? So yes, the number one rule of progress in physics is to do the dumbest thing first. Okay? 90% of the time it works. And then the 10% of the time it doesn't work, you learn something valuable, which is that the dumb thing doesn't work, which is very important. Okay? So, all right. Oh, sorry, not equal to 0. Just that is the line. This is the line. Right? That's really cool, right? Okay. Now, let me do something even scarier. Let's say I have a conic. I have a point that's not on the conic. So this is some x that's not on the conic. But it's natural to draw the lines to the conic from x that are tangent to the conic. Right? So they meet the conic at these 2 points. And now I could want to know what is that line. Okay, so now that's the new problem. Yeah, so what is it? It's the same. Exactly the same formula. This line is also Cij xj. It's just that here we could check that x star was on this line, simply because if I multiply Li x star I, it's equal to C x star, which is 0, because x star was on the conic, whereas here it won't be 0. Okay. All right, but let me do a final thing. Let's go back. And let me write down the following equation. Cij xi yj equals 0. So let's say I have a pair of points, x and y, such that cxy is equal to 0. Right? So what does that mean geometrically? Okay, it means that this was the line cx, right? So it means that y is somewhere on that line. Right? Okay, so that's cool. So we learned that y is somewhere on this line. But I could have also read this equation as x is on cy. So we learned something. That if I draw these tangents from y, and I get this line, that x is on that one. Right? That's really beautiful. There's this symmetrical pairing between 2 points on off the conic, such that if a point y is on the line made out of the tangents from x through here, then x is similarly on the line attached from the conics through there. Right? So, so these are just trivial statements. So we're doing nothing other than just algebraically playing by grouping things together with indices however we like. And we get nice, true geometric statements that are easy to work with. All right? All right. Now, let me tell you some more practical things. So here we are talking about two-dimensional projective geometry. In the amplitudes business, of course, you often need to think about much higher dimensional projective spaces. And so let's just talk about some very simple things. So let's already go to P3. Okay? If we go to P3 again, if you want to visualize, just think about it like points, lines, planes in 3 dimensions. Okay?
Was this P2?
Yes. This was all P2. This was all things in the plane. And remember, the number of indices is always one more, right? So we're in P2, but there are 3-dimensional vectors. Okay. So let's go back and do exactly the same things. What's going on in P3? So I can have points that are xi, right? Now, what are things with downstairs indices? What I was calling Li before. Maybe I'll still call them Li. No, I shouldn't call them Li. Wi, let me now call them. All right, so what are these going to be? Hyperplanes, exactly. Sheets, hyperplanes, just, well, planes, flat planes here, okay? Okay, good. So now we can again ask the same kinds of questions as we did before. For example, how can I specify a plane? I can specify a plane by giving 3 points that are on the plane, right? So if you give me 3 points A, B, C, the 3 points define a plane. Which plane is it? Okay, so if you give me A, B, and C, now I'll draw a picture like this, but there's 3 points A, B, and C on this plane. Then the W that goes along with this plane is epsilon I, J, K, L, A, I, B, J, or A, J, B, K, C, L, right? Which we could also write as A, B, C, again, downstairs I. Okay? Now, it's actually useful to kind of more uniformly think about planes of a given dimensionality, all with indices upstairs. Okay, we can of course always use the epsilon symbol to move things up and down if we like, but it's just a more uniform way of thinking about it. So, and here we actually see its use, because what is a line? What is a line here? So let's say you just give me an A and a B. What can I do with an A and a B? An A and a B, I can just make a 2-index antisymmetric tensor out of them. Okay? So see, a wall is a 3-index antisymmetric tensor. A wall made out of A, B, C, I just wedge them together, A, B, C, and I antisymmetrize. Okay? So if I leave all the indices upstairs, a k-dimensional a k-1 dimensional object made out of k points is just the antisymmetric product of those k points. Okay? So, but let's just check that this thing about the line really works. Again, it sort of obviously does, but a line in 3 dimensions is something that's antisymmetric in 2 indices upstairs, and a line made out of 2 points A and B is just A, I, B, J antisymmetrized. Okay? So first let's check, are A and B on this line? Well, yes they are, right? So I put another A there and I contract everything with the epsilon symbol, then they are, right? But there's a deeper reason why they had to be this antisymmetrized combination. And that has to do with, you know, what a line is, right? See, if I just give you 2 points, A and B, that are defining the line, the whole point is that I don't want to have this be a line with 2 marked points A and B on it. I just want to keep track of the line, right? So that means that I should be able to take A and send it to any linear combination of A and B and get the same object back. So when I choose to label the line by 2 points on it, that labeling is introducing some arbitrary reference things on the line, but I want the line itself to be independent of how I choose the labeling, right? So this should be invariant under A I as a vector, and B I goes to any 2x2 linear transformation on A I B I. Okay? If I do such a 2x2 linear transformation, I should find that my object goes into itself. And it does, when these guys are antisymmetrized, right? So what does this do?
And scaled correctly.
That's right. When I do this, when I do this transformation, L goes into itself multiplied by the determinant of this 2x2 matrix. Okay? That's why the antisymmetrization matters. Okay? For example, let's say I didn't antisymmetrize, just did AI BJ. Apart from it looking stupid and not satisfying that dotted into A or B gives 0, what's wrong is that if I rescale A goes to A plus something times B, it changes, right? But this goes into itself up to a multiple. And remember, this is all projective. So L and anything times L is identified anyway. So it's okay to go into itself up to a multiple. Is that clear? Right? So that's why planes of various dimensionalities are just given by wedging together. If you have k objects to make a k plus 1 plane, you just wedge together. Sorry, k objects to make a k minus 1 plane, you just wedge the k of them together and keep all their indices upstairs. Okay, so now let's in this language talk about various nice solutions of various nice geometry problems. So,
Question?
yes.
Should we think it's weird that we now have the blind indices upstairs?
No, that's what I said, is that we can always choose to have all the indices upstairs. Even in the P2 story before, because it was so easy and familiar, we were just going up and down. But more invariantly, I mean, just convenient to always have the indices upstairs. You can always move them downstairs with the epsilon symbol. But if you keep them all upstairs, it's easier to keep track of the dimensionality of the objects that you're talking about, and to do the exercise I'm just about to do for you. Okay, so, all right, so let's do a few more little examples. And yeah, in 15 minutes you will know as much about projective geometry as I do. So, so then I'll have to stop talking. Okay, so let's say you have a plane and a line. Okay, so a plane intersects a line and a point, right? So what is that point? All right, so now this wall has a let me keep giving it a downstairs index here. This line has two upstairs indices. So what is that point? Again, all it could be. This point is Wi, L, Ij. Okay? That's this intersection point. So we could call this, you can use this notation, L intersect W. Right? L intersect W now gives you something in this case, but what does this notation mean in general? It means you write whatever this sucker is with all upstairs indices, or however you want to put the indices, whatever it is, whatever that is, and you epsilon them together. Okay? And in this case, what you get is something that's left with an upstairs index, and that's the intersection point. Okay? What if you do something else? What if you have two planes, plane 1 and plane 2? Two planes intersect on a line. What is that line? Well, again, trivially, it's just W, W, and you epsilon them together, which now gives me two upstairs indices. Remember, here it's a 4-index epsilon symbol, right? I don't know if I said it explicitly, but okay? Now, what if I take two lines? What can I say about two lines? I can take two lines and I can just epsilon them together. So now the only question is, are these two lines, are they coplanar? Do they intersect each other or not? Okay, so that's the only question I can ask in 3 dimensions about two lines, right? So let's say I have a line here, and I have another line, L1 and L2. And I can just write down L1, L2, which is just epsilon ij kl, L1 ij, L2 kl. And this measures, if this is 0, the lines intersect. If it's not, they don't. Okay? L1 equals 0 if the lines intersect. Let's say I characterize the line A by some A and B, and the line 2 by some C and D on the line. Then what is this bracket? This bracket is just A, B, C, D. Right? And of course, that independently is the measure of whether A, B, C, and D are coplanar with each other, right? Because A, B, and C defines the wall ABC with a downstairs index, and I'm checking whether D is on that on that plane. Okay? So if ABCD is equal to 0, they are coplanar, and it's the same condition. Any questions about this? Yes?
So for some reason we can't ask about the point of intersection if they are coplanar, because it doesn't look we can construct anything which is a point.
Oh, that's a very nice exercise that I'll leave you to think about. Okay? Yeah. So yeah, that's well, I could answer it, but let me not. try to do it yourself, right? Okay, maybe I'll say one more thing and then we can take a little break. There's a very obvious thing that we're so familiar with, we've been talking about like it's nothing, that we can of course describe things with either all upstairs indices or all downstairs indices, right? But geometrically, that turns into a kind of a remarkable statement. Let's say you have any fact about some configuration of points, lines, planes, any fact you like. That fact translates to some statement about objects with upstairs and downstairs indices. Or maybe all upstairs, all, it doesn't matter, right? But now, just if you flip all the upstairs indices to downstairs indices and vice versa, nothing changes in all those invariants. That's a completely obvious symmetry of the problem. But that is a remarkable geometric statement. It's the oldest form of duality known to humanity. I think it was discovered first by Desargues, one of the early projective geometers. But it's a remarkable statement that in projective geometry, any statement, for example, in two-dimensional projective geometry, any statement you make about configurations of points and lines, if you interchange the word point with line and line with point, you get another true statement. Okay? So most trivially, any 2 points define a line, true. Any 2 lines define a point, true. Okay? Less trivially, take that statement about Pappus and dualize it. Okay? That's much less obvious. It says, given 3 lines that go through a point and another 3 lines that go through a point, you find 3 other sets of points, build lines, and those 3 lines pass through the same point. Okay? Now when you say it like that, it's very unobvious. Okay? It's not an obvious, purely geometrically it's not an obvious statement, but from this algebraic way of thinking about basically the fact that, SL has the trivial symmetry, taking L to L inverse, and is projective duality. Okay? So similarly in 3 dimensions, any statement about points, lines, and planes, if you interchange what you mean by plane with point, and line with line, which is lines are self-dual, you get another true statement. All right? Okay, and finally, this way of thinking about things makes it very convenient to do geometry in higher dimensions. Okay, so let's just do a random example. Say I give you, say I give you a 2-plane, say I give you a 2-plane in, so there's some 2-plane X, so this has 3 indices, okay? I give you a 2-plane in 7 dimensions. And let me just choose anything else you like. Let's say also a also a 4-plane. Okay, remember, always the number of indices is 1 more than the dimensionality of the object. Okay? So I give you a 2-plane and a 4-plane, both in 7 dimensions. How does a 2-plane and a 4-plane in 7 dimensions intersect each other? Now you could sit there and think, and but the point is not to think, right? So all you have to do is just count the indices, right? Just write them and just see how many indices, after you epsilon to your heart's content, how many indices can you be left with. In this case, I have a total of 5 plus 3 is 8 indices. I'm in 7 dimensions. Maybe I should have done 6 in P6. P6. So that means that that my epsilon symbol is 7-dimensional, and so I could be left with a point. Right? In other words, if I just take x, y, epsilon together, I'll be left with one index upstairs. Okay? And so once again, you have this notion x intersects y. Okay? X intersect y is now something that has one upstairs index. Okay? So it is a point. Okay, and what if we had done what if we had made this anyway, you can see. So if I made this a 3-plane, still in P6, I have one fewer index, and now these guys will intersect in a line. Okay, I'll have two things left over upstairs, and so on, right? So, oh, sorry. Sorry, no. So I did it backwards. So in this case, yeah, sorry. So in this case, all I can ask is whether these things intersect or not, right? In this case, I have the same number of indices. So x and y do not in general intersect, but if x, y contracted is equal to 0, then x intersects y. Okay? Yes?
If you've got one leftover index, how do you know whether it should come from the 2-plane or 4-plane?
The epsilon symbol just takes care of it. You have one giant epsilon symbol, and it just it takes care of all of them. Okay. More things along these lines. So, okay, anyway, so just figuring out how objects of various dimensionalities intersect each other is just a matter of counting indices and contracting with the epsilon symbol in any way that you can. Yeah, I guess the final very basic thing that I'll say is let's say you're in 3 dimensions. And you have a bunch of points. Let's say you have some, and I'll call them Z1, Z2, Z3, Z4, and so on, right? Now, these are, if I'm in P3, these are 4-dimensional vectors, right? So you can take a 5th vector and write it as a linear combination of those 4, if you like, right? So how do I find how to do that? So I want to take Z5 and write it as some alpha 1 Z1 plus alpha 2 Z2 okay? Well, all you do to isolate 1, you can just contract this with 2, 3, 4. So that would give me 5, 2, 3, 4 is equal to alpha 1 times 1, 2, 3, 4. Okay, and so on. So that lets me solve for alpha 1 and all the rest of them, right?
A little more directly, you can just talk about a 0-plane or something.
That's exactly what I was going to say. Okay, so I was doing it directly, and then I was saying that. We can think of this as a special case of this intersection formula. Okay, so but if we just do it, if we do it in this way, this is just the statement. If you take any 5 points, 1, 2, 3, 4, 5 here, because we're doing it in P3, that we can write. So you just take 1, 2, 3, 4, 5, and you go through deleting one of them at a time, pulling it out, and writing the bracket for the rest of them. So we'd have Z1I. 2, 3, 4, 5 minus it's anti-symmetrized, so minus Z2I 1, 3, 4, 5 plus Z3I 1, 2, 4, 5 minus Z4I 1, 2, 3, 5 plus Z5I 1, 2, 3, 4 equals 0. Okay. So this is variously known as Cramer's rule, or the Schouten identity, or there are many ways of saying it. And actually, what I want to do, but Jake, gave it away, thanks a lot, is I want you to interpret this formula geometrically. Okay, so ignore what he said. I want you to interpret this formula geometrically as telling you about a statement about a certain intersection. Okay, so it has a very, very pretty and simple statement as an intersection. But just to give another, actually a fancier application, but just to show this in action. So let's say I want to know in 3 dimensions. So let's say I really want to do the exercise. I have some plane ABC, and I want to intersect with another plane DEF. Okay, so this is a plane that has 3 points ABC on it. There's some other plane, so they're going to intersect on a line, right? So I just told you how to do it, abstractly with the epsilon symbol, but what does it really mean? Okay, so this is now something that I have to get with 2 upstairs indices, right? It has to be a line, so it's just AB, 2 upstairs indices, times CDEF minus AC times BDEF plus BC times ADEF. So is it clear how that worked? I chose to in doing the epsilons, I can just take this side, and I just pull out all the pieces. That has to be anti-symmetric. So this AB is something with 2 upstairs indices. So I'll write for the last time explicitly like that. Okay, but this is an expression of that intersection. See, it's very beautiful. It just tells you explicitly what you mean, and just calculate that line. Okay, now you could have said I could choose this one, and that's fine. That would give you another 3-term formula, and the equality between these 3-term formula is the Schouten identity. Okay, so I'm giving away, as Jake did, to interpret this formula, what you want to do is move various terms around on the right-hand side and the left-hand side, and interpret that in exactly the same way as a certain intersection of 2 objects viewed from the perspective of one or the other. Okay, so you can have a line intersecting a plane, or the plane intersecting the line. And depending on how you expand, you get the formula with the set of terms on one side or the other. Okay? So you can think about, but do it yourself. You can think about this as the intersection. You can think about these first 2 terms. Think about these first 2 terms as actually the intersection of the line 1, 2 with 3, 4, 5. That's a point. Okay? And so the intersection of 1, 2 with 3, 4, 5 is either this one or it's negative of that one. Right? Okay, and you should work through that little exercise yourself. Okay? Okay, I think that's it. Should we take a little break? And all right.
So the food, the lunch arrived earlier, but we are not eating yet. Yeah.
That's very dangerous.